Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
Good afternoon, everyone. This is the EESN webinar for August. I am the network chair for the MIT Alumni Energy, Environment, and Sustainability Network. We call it EESN because we have such a lovely name. I'm Sarah Simon, class of 1972 in course 1, civil. It wasn't environmental at the time, which Diane McKnight, one of our speakers, can also attest to. But I did study water resources and stuff. EESN is a worldwide network of alumni groups and alums, and we created this to educate and inform people about the complex, interconnected, and dynamic challenges of energy and environment. You often we hear it called climate change these days, but we've been all working on this a long time before people were more aware of climate. We were also created to connect and highlight our talented and creative alums, like the speakers today. And we also like to connect alums so that we can support alumni and groups in taking action on all of these things, on finding solutions and implementing solutions to the problems. So this is a webinar Zoom format today. We do not have the chat activated for you in the audience. We will be able to post links and things from the panelists. There will be some information in the chat about general things, but we encourage you to put your questions into the question and answer section. We will get to those after the presentations. And so that's the way we're going to communicate. This session is being recorded, which I think you were probably told when you joined Zoom. And we will be able to post the slides afterwards. If you go back to the event description page on the EESN website, the slides will be posted there, and the video and recording should be posted there before too much time passes. We like to caption it properly. MIT always likes to have Americans with disability captions, so that it's all right and the names are spelled right, for example. But anyway, onto the webinar. We have 3 really fun and interesting alums with us today. I'd like to start with Diane Diane McKnight, who I've known for some time. She originally had a mechanical engineering degree, but then went into course 1 and got one of the very first environmental engineering PhDs at MIT in 1979. She was a research hydrologist for the USGS and did a lot of work up at Mount St. Helens after it exploded back then. So she's very expert in acid rock drainage. And also, after having become a professor at the University of Colorado, she is a National Academy of Engineering member. She was appointed to the National Academy. And so today's work that she's doing looks at a lot of the ecosystem and water quality changes in the Colorado mountains. Temperatures increasing and the old mine drainage and the rock weathering has all changed and all affects the ecosystems in many ways. Gia and Abe Schneider, I'm going to put you together. Our sister and brother who grew up in West Texas, as Abe was telling me. I don't know if it was West Texas, but it was on a Texas farm. And they loved playing in the creek and developed a real love of and connection with the ecological world, with the real world. I like to talk the natural world. Let me put it that way. Gia was a course 10 graduate and then went out of school right into consulting at Accenture in their utility businesses. And at that time, they were beginning to look at renewables, and she wanted to know how it worked. She has worked for other utilities and also for financial firms like I believe she said Credit Suisse. She worked with them on price risk and weather. And then after working at it was the carbon desk at Credit Suisse, and the price, risk, and weather may have been at one of the utilities as well. I could have that mixed up. But anyway, after doing that, when brother Abe Schneider came along to do some business and work and wanted to be an entrepreneur that made all these things come together, she and he founded Natel Energy, which we'll hear more about today. So Abe grew up in Texas on a farm, loves entrepreneurship, and was a 3-degree MIT kid. He likes to make things, to solve difficult problems, and he always loves looking at new angles and new approaches to the answers of how you get there. Thermodynamics and fluid dynamics are his thing. He just really likes that. So he did work for a company, Timken, that does bearings and steel, and he was in their R&D office. And he also worked at a company that was backed by Alphabet, by Google, that was doing airborne wind energy. And then it worked out for Abe and Gia to start Natel. So with that, we're going to start with Diane speaking and doing her presentation. Then Abe and Gia will talk about how their company and the way they design works with the environment and to make hydropower that's safe for fish. And then we will open a question and answer period. So please, along the way, put your questions in. Thank you very much. Great. Diane, it's yours. Why don't we put your slides up?
Yes, I'm putting my slides up right now. It's a pleasure to talk with you. And I'm sorry I put my slides up at the end of the presentation. Now I'm at the beginning. So I'd like to start off by explaining my role here is to present kind of a context for the innovations that Abe and Gina will be talking about. I'd like to think about the role of dams in river ecosystem modification and point out that the human race has been modifying river ecosystems and the flow of water from one place to another for a very long time. This is a picture of the aqueducts, which are actually thought to go back to the 6th century. We can apply modern understanding of how river ecosystems work. There was a important paper called the River Continuum Concept that was published in 1980 that thought about how river ecosystems change downstream. And for example, if we think about the Mississippi River at New Orleans, it's a very muddy river. There's songs about that, and that changes the light attenuation and whether the river is photosynthetic, for example, whereas also upstream, the shading of the rivers by trees in forested catchments also limits photosynthesis. So within this framework, dams represent a discontinuity in this river continuum because the sediment settles out, there's impoundments with a lot of open water and potential for photosynthesis both in the reservoir and also in the clear water downstream. So the US has 14% of the world's largest dams, and there are over 2.5 million dams, and many that are greater than 5 meters and also greater than 15 meters in terms of height. Most dams in the US are privately owned. So if we think of this collectively, this is an old quote from Bruce Babbitt. We have been building on average 1 large dam a day every single day since the Declaration of Independence. So that gives you a sense of the scale at which dams have been built in the United States. Hydropower is certainly a very important goal for dam building. 31% about of the US power comes from hydroelectric. This is a picture related to the Colorado River. Another important role is impoundment of water for irrigation and agriculture. In Colorado, 80% of water used in Colorado is for irrigation. And that's also true in California. And another important use is for recreation. And there's a picture of a big fish and riverboats. So many people value the recreational opportunities provided by reservoirs and these impoundments. Another important goal in terms of dams is for flood protection. Obviously, floods can cause severe damage. We've been hearing a lot about this around the country over the last several years, and the dams can be used to buffer against large flows. One of the exacerbating issues, however, is people have developed and cities, homes, and such in traditional floodplain areas, so that if there is a failure of the dam, there's high risks. And we can look at the history of dam building. This is from an old paper and shows that between 1950 and 2000, we can think of this as a golden age of dam building, a pace of 700 per year. And these lines show the heights of the dams. And now we're in this phase where there haven't been as many being built. There are ways in which the dams clearly change biological processes in rivers. We have the inundation of habitat, reducing river levels, and altering the timing of flows by holding water back. In some cases, rivers have gone from being not perennial, intermittent rivers to being perennial. And also there's an increase in water temperature as that surface water of the reservoirs warms up. And these dams also clearly retain gravel, woody debris, and nutrients and such. In the context of fish, which is one of the themes here in terms of enhancing fish and aquatic organism survival, the passage through a reservoir can delay the juvenile migratory fish's journey to the ocean and cause physiological issues as well. And also there can be new predators and issues related to high water temperature and disease. So another context here for this discussion is that there have been many recent examples of recovery of aquatic ecosystems and fish in particular after removal of dams. And this are just a few examples shown here. But the Elwha River is one of the most commonly cited examples where two large hydroelectric dams were removed. And I've got a link into a video about this. But clearly, not all dams have to go. And I don't want to leave you with that impression. Many continue to serve public and private functions, again, flood control, irrigation, hydropower, but many could be operated in a fashion that reduces some of these negative impacts. This idea of, well, let's be smart about it. And again, we can think about which dams are ones that need to be enhanced in some ways. Thousands of dams were built in the 1930s and 1940s, and I said 1950s and 1960s, and they're nearing the end of their design life. And some of the issues have to do with sedimentation. So as I mentioned, the woody debris and the sediment doesn't make it downstream. It accumulates in the reservoirs, and the reservoirs lose capacity compared to their initial conditions when they were built, when the dam was built. And then the other issue is clearly degrading concrete and degrading infrastructure more broadly. I like to point out that most civil engineers know that concrete doesn't fix itself. And another issue to highlight is that dams were designed based on a concept of stationarity of hydrologic variability. That's this idea, well, this is the 100-year flood, this is a 500-year flood, where we can use the records of the past to know what's the likelihood of a certain flood occurring. But since 2000, there's been recognition, and a great deal of publications have asserted that this concept of stationarity is dead. It's not useful anymore. And I have a link here to a video from a Bureau Rec video about called Challenge at Glen Canyon, this 1983 event where there was a high snowpack and then rain on snow, and they almost lost the Glen Canyon Dam, which is just unimaginable to think about. So now the recognition is that stationarity is a zombie, because this idea of stationarity was not only used in terms of actually building the infrastructure, but also the regulatory constraints with water rights and such are related to this old idea. So other issues that you may be aware of is falling reservoir levels threaten important uses such as water supply and recreation. And many of these dams have not been well maintained and pose risks to downstream communities under what we can think of as deep climate uncertainty. For example, the atmospheric river phenomena that was so important in the context of the climate or the weather in California recently. So this results in some hydropower plants not being able to be operated at full capacity. And the outflow, another issue in the context of climate change, is that the outflow of bottom waters from released from the reservoir can release methane, which is a potent greenhouse gas, because methane accumulates in the bottom waters of these reservoirs, and this can counteract some of the green benefits of hydropower. Clearly, there has been approaches for enhancing the survival of fish in the context of fish migrating upstream. The fish ladders have been improving. Some of these dams that come up for relicensure will be adding fish ladders, but there are challenges that also need to be considered. And I want to just point out that in general, there's a range of considerations so that this can be approached reservoir and dam one at a time. You know, there's no general approach for what to do, but the context and what are the uses, what are the extent of degradation, all make an important component. And innovations on the engineering side in terms of these turbines is very important. The Bureau of Reclamation has been upgrading their turbines over the years at Glen Canyon, for example, and obtaining more power for the same amount of water since the Glen Canyon Dam was first built. So I'm going to stop sharing my screen, and hopefully that was a brief intro to what will be talked about next.
Okay, and thanks very much, Diane. That was really, I think, really great context for what is a very multidimensional and I think very interesting set of challenges that we face in hydropower, in part because hydropower is this very amazing, reliable, renewable energy resource from an energy production perspective, but we obviously have a lot of legacy infrastructure and a lot of legacy environmental issues that we need to address, all layered on top with the overall kind of macro challenge of how do we tackle both climate change and biodiversity loss, both which are kind of like the critical existential things, if you will, that we face and that we need to tackle. Let me just share our slides. And so what Abe and I are going to talk through today is to share a little bit about what we are doing at Natel to tackle these twin challenges of how do we address some of the sustainability issues in hydros, particularly around fish and river connectivity, while also enabling these assets to have another several decades, at least in many cases, more of renewed life. As a company, we're based out in the Bay Area, in the San Francisco Bay Area. We're a team of about 30 folks. Really, a lot of we are fortunate to have a strong contingent of MIT engineers and folks as part of our team. Just a quick background about a little bit more context for Abe and I, and we've had a long history of focus in climate and renewable energy issues at the intersection of with energy and water. And it really just started with our father. He was very focused and motivated by the energy crisis in the 70s, as a lot of folks were, frankly, in developing technologies now that have really started to scale in wind and solar. And so he grounded us in some very early awareness in our childhood of climate change as a really critical issue that we need to address. And that fundamental to that is, how do we evolve our energy infrastructure so that we go from burning this stored sunlight in the form of fossil fuels that was laid down in the age of the dinosaurs, and go to taking energy from direct sunlight and then the embodied energy of effectively sunlight in moving wind and water. Additionally, as was mentioned, I think in the intro, Abe and I, spent a lot of time outdoors and have a very strong connection to the natural world, a strong connection to water. And Abe actually did some really cool research as a teenager, looking at biodiversity impacts of nature's engineers, beavers, in beaver dams in particular on rivers. And so there's a longstanding interest in this space. Well, from some grounding context for hydro from an energy supply perspective, hydropower today is the third largest source of electricity behind coal and natural gas globally. It is a major part of our energy supply, or of our electricity supply, to be accurate. We have about 1.3 gigs installed globally, and it's, again, about 50% of the renewable or zero carbon energy supplied today. It also is a really interesting source of flexible power. So a number of studies have really highlighted the fact that a gigawatt or 1 megawatt, 1 unit of hydro basically is able to firm, somewhere from 3 to 5. Some studies show higher than that, but we like to just use this kind of one unit of hydro helps firm 3 to 5 units of wind and solar. And as we drive to a zero carbon grid, particularly given the fact that we have a lot of existing hydro on the grid today, figuring out how we modernize and upgrade and get more out of that existing hydro, given that it's already interconnected, we don't have to build it new, we don't have to go through, a 5-year, in some cases, interconnection process. Figuring out how we can do those upgrades is really critical to accelerating the energy transition. In addition, we want to unlock new growth. So how do we get new hydro on the grid? And to do that, we clearly have to move the needle from an environmental perspective. Another really, just a couple data points that I think are important to understand some of the nuance at play is that even in drought, so out here in the West, we are seeing hydro play a really critical role from a grid reliability perspective. And I think that, again, this issue gets many layers that you have to dig through to understand what are the right trade-offs and choices to make as we modernize the existing fleet. So what you see out here in the West is basically, even in drought, hydro is dispatching right alongside natural gas day in, day out to balance the grid. And that is directly a result of the fact that hydropower is kind of a premier reliability, flexibility resource alongside natural gas, just from a pure power generation, power systems perspective. Another interesting data point is in 2020, another very severe drought year here in California. We had 2 weeks where the grid here almost blacked out, and hydro was 2/3 of the reliability resource that kept the grid in California on during that really critical period of time. And it was just because hydro can time shift. So it was able to dispatch down in the middle of the day, dispatch in the kind of witching period, which is the evening hours out here, are the particularly tough ones to deal with, because solar tapers off, and obviously we still have peak load. So just some context. as we think about the challenge that we set out to solve, it's this combination of how do we take the old fleet and modernize it while meeting modern environmental requirements, particularly around fish passage. And then where we are thinking about building new, which is in general mostly not here in the US, how do we show a pathway to do that new build in a way that takes all these lessons learned and really does it in a much more sustainable, climate resilient way for the future. Some numbers around the aging fleet. We've got, basically when you look at the aging fleet problem is exacerbated by the fact that we have a lot of old plants that are at the end of their license life. So we have a lot of assets that are coming up through relicensing in the next decade that also are 60 years old, 65 years old with old equipment that needs to be upgraded. And that is kind of the really very specific impetus, or if you will, or market demand factor that is driving the uptake of the work that we are doing. To bring that home to a very specific case around the regulatory driver for fish, and in this case to focus in on eel, there's about over 30 gigawatts of the US hydropower fleet directly overlaps with critical American eel presence. And unfortunately, conventional hydropower is very eel unfriendly, to be blunt. And so you might, and as a result, we've really seen, pretty abrupt, unfortunate tapering off or really crash in the eel population over the last couple decades. So you might ask, why do we care about eel? And the reason we care about eel is because eels are a very critical part of the life cycle for mussels, for freshwater mussels. Why do we care about freshwater mussels? Well, freshwater mussels improve water quality. And we have seen, again, over the last couple of decades, some really major water quality issues in our rivers. And those are obviously not good for the broader environment, but they also have some very specific impacts on humans. And so at the end of the day, I think we like this example because it really helps illustrate how we can engineer solutions. If we have the right drivers, we can apply our engineering skills to develop technical solutions that actually can help unlock a cascade of natural infrastructure or natural improvements as well. We just have to understand the relationships, how these things all go together. But as I said, eel, unfortunately, don't interact very well with conventional hydropower turbines. So it's unfortunately just the result of the way conventional turbines are designed. And so we set out then to answer, can we make this better? And I'm going to turn it over to Abe to talk us through.
Thanks. Yeah, so one of the biggest reasons that eels aren't very compatible with hydropower turbines has to do with their shape. So eels are long and skinny and kind of like a snake in their form. They can fit through places that a lot of other fish wouldn't necessarily be able to make. But also they migrate downstream as adults. So I think a lot of the public, if you were asked, tell me a fish that might come into contact with hydropower, and the first response might be salmon, which is true. There's a lot of issues around salmonids and hydropower. But certainly on the East Coast, eel are the ones driving hydropower regulations and operational curtailments. And they have this unique life history where they migrate upstream as babies. They stay in freshwater for years, grow large, and then they need to go downstream as large adults, sometimes 3 feet long or longer. So when fish are passing through turbines, especially turbines that look like the ones on the screen here, they're subject to a couple of primary stressors that can lead to injuries or to mortality. And first and foremost are mechanical. So direct strike with fast moving and thin blades, but also fish can get stuck between parts that are moving and parts that are stationary. And in particular, some kinds of hydropower turbines have geometries that really exacerbate this risk quite a lot. In addition to these mechanical stressors, there are pressure-related injuries where fish that are acclimated to the bottom of a reservoir get basically decompressed through a turbine very rapidly and develop air bubble disease and other barotrauma-related problems. But for the most part, low head turbines primary source of danger for fish is mechanical in nature. And these are problems that Natel has really focused on in finding engineering solutions to allow for safe aquatic organism passage. So we've started from the really big picture, and now we're going to zoom into the extreme details of how do you actually design a machine that's safe for organisms. And I think that as I describe this, consider other industries that have successfully included the physiology of living organisms in their machine design. So for example, cars and planes and boats are all designed with one of the first and most important criteria being the safety and survivability of humans. In automobiles, we've been very successful in designing cars and car technology to reduce the likelihood of crashes, but you can never reduce that likelihood to zero. And so you've always got to be able to allow for humans to walk away from a crash and live another day. And in hydropower, that really hasn't been first and foremost. The first and foremost design criteria in hydropower historically has been efficiency or cost or longevity. And so Natel is really leading the field in terms of prioritizing fish safety as the first and foremost design constraint, and then allowing all the other factors follow from that. Okay, so if we are trying to design a turbine that's safe for fish, someone once told me that, oh, this is very easy. You just make the turbine really slow. So you could make a turbine from razor blades, and it'll be safe for fish as long as you move it slow enough. And while that's true, it doesn't really solve the problem that we have a large existing hydropower fleet, and you're not going to be able to retrofit that big asset base of hydropower plants with really slow moving turbines. So we have to design turbines that are compatible with the hydropower of today. And that means designing turbines that spin fast at exactly the same speed that our conventional turbines are already operating at. And in other respects, also basically allow for replacement of existing conventional runners in place with runners that are safe for fish. So how can we design runners that can allow for a fish to contact the blades and then survive? One of the key engineering parameters that has been known about for at least 10 years is a ratio between the length of the fish that are expected to pass through the turbine and the blade thickness. And that's what we're illustrating here in the top left. As you decrease that L to T ratio to something around 1 or 2 to 1, it maximizes the survivable strike speed. But prior tests have shown that this speed is around 7 to 10 meters per second, and conventional turbines have strike speeds that are 2 or 3 times that value. So we needed to find some additional way to allow for a further maximization of safe rotating speed. And our basic thesis is quite simple. It's that the forces affecting trauma in a fish, given a strike, are proportional to the orthogonal component of the relative velocity at the point of contact. And that's what we're illustrating in this cartoon in the lower left of this slide. The red vector is what is proportional to fish trauma given a strike. And if we're able to basically arbitrarily control the angle of the blade surface, we can arbitrarily reduce the magnitude of that vector. Of course, like all engineering problems, there are trade-offs in terms of what's mechanically feasible versus the benefit. And in this case, a slant angle of about 30 degrees allows for a reduction in that normal component by about 50%, while still allowing a mechanical part that could be constructed. And the end result of this design approach is a turbine that looks like the ones on the right, where the leading edge is progressively swept more and more forward at greater and greater slants as you go towards the outer radius of the machine where the strike speeds are highest. And the link on this page summarizes a series of nearly 2,000 live fish strikes that were done to test this hypothesis. So these strikes have actually given us a quantitative basis, basically a dose response curve that allows us to computationally design new and arbitrary turbine shapes with fish physiology as a driving design constraint. Okay, so what do turbines look like that use this type of input? Here's an example. This is a 2-meter diameter turbine at its full rated head of 10 meters. This turbine would produce about 1.5 megawatts. One of these units is installed in Oregon, and there should be a handful of these going into a new project in Africa sometime in the near future. But this is just one example of what a turbine could look like. In the world of hydropower, there's quite a variety of intake configurations and outlet configurations, but they all basically have a component that spins and extracts the work from water, and that's what we're designing to be safe for fish. So there are 3 units currently operating with runners following this design principle. I should mention that we began work on this idea in 2019. So everything that you're seeing has basically been accomplished since then. There's one unit in Maine, a small unit in Maine at an old mill, which has been rehabilitated with a fish safe turbine. And then there's one in Oregon, shown here in the middle. And then excitingly, our first unit in Europe was commissioned in October last year in Austria. There's another unit that should come online in Virginia, potentially later this year. And I'll talk about some of the very exciting, much larger machines that are up and coming. So Natel has invested very heavily in testing of its turbines, and specifically and uniquely in testing the success of passing fish through the turbines. We're based in Alameda, California, which is right across the bay from San Francisco. This is an aerial photograph of our in-house hydraulic testing facility. Basically, water is pumped in a counterclockwise fashion, as shown by the orange arrows, through a turbine, which is about 21 inches in diameter. The test stand is capable of supplying about 100 kilowatts of turbine power. And it's designed to allow for extremely high precision measurements with less than 0.5% experimental uncertainty. This is all sort of fairly conventional. If you go back one second, for the hydropower industry, what's really unique about this is that we can introduce fish into the pipeline, allow them to pass naturally through the penstock, through the turbine, directly be observed with high-speed video cameras, and then be extracted and inspected for their condition within seconds of passing through the turbine. And this is something that we have now been doing for roughly 2 years continuously with over 6 different species of fish, including eel, trout, warm water species like bluegill and bass, sturgeon, catfish, and the list is increasing. We've also cultivated really strong collaborative relationships with national laboratories, with local universities, and with fish farms in carrying out all of this work. So the next couple of slides, I'll show you some specific examples of fish passage tests that we've conducted. First, here's a video of eels passing through our unit, the unit that it showed on the prior slide. This is a passage test that we conducted with the Pacific Northwest National Laboratory. The entire test is summarized in detail in the paper linked on this slide. Top line, really exciting results are we were able to pass eels with 100% survival, 0 mortalities under extreme conditions, never before seen. So these are eels that were up to 65 centimeters long, being passed through a turbine that's only 55 centimeters in diameter at 10 meters of head and 670 RPM. So if you think about how fast that is, this is an extremely fast rotating turbine with really large animals passing through with no mortality. And really importantly, because we're directly observing passage, there's very, very little uncertainty as to what's actually happening inside the machine. This is something that really hasn't been done before. We captured about 90% of the individual specimens in the test, and we're able to learn quite a bit about the kinematics of the fish passing through. So next slide shows a similar test, in this case done on a plant on a wild stream in Maine. These are juvenile alewives. So alewives are in the shad family or the Olocene family. And they're one of the two species really driving hydropower regulations regarding fish passage on the East Coast. Folks who attended MIT probably were on the T and heard the word that, the alewife station. Well, that's in reference to these fish, which have a really important historical, cultural context in the region. These fish are extremely delicate. They're sort of famous for dying if you look at them funny. But we were able to design a test which allowed for 100% recapture of these fish without any need for tagging, which helped to reduce handling trauma. And we observed between 98 and 100% control corrected immediate and 48-hour survival. And also were able to capture this amazing high-speed video of the fish basically just sort of raining through the turbine and not really being struck in a violent way by the blades, which is what we would expect for fish of this L to T ratio. So the next slide is the last one that I have to show an example of fish survival testing, in this case done with rainbow trout. We've done 2 different sets of tests in collaboration with the Pacific Northwest National Laboratory on our small plant in Oregon, which is the 1.9 meter diameter turbine. And we've tested trout up to just over 50 centimeters in length, which for anyone who's a fly fisherman, this would be a lifetime trophy rainbow trout. And in our in-house test facility, we've tested trout as small as just over a couple of inches, up to over 10 inches through a 55 centimeter turbine with 100% survival in all instances. And so I think one of the overarching points of all of this is that we're approaching fish survival from the perspective that it's not just one species and it's not just one life stage. We're trying to design turbines that can allow all aquatic organisms that could get entrained into a turbine safely. And this really represents a generational opportunity in that we have this simultaneous need to relicense, but also to rehabilitate our aging hydropower fleet. And it's a fantastic opportunity to make wise decisions and replace these old turbines with turbines that are safe for fish for the next 40 to 50 years. Now is the time to make those good decisions. And then just as a bonus, I wanted to show you, since we're all engineers, we like looking at really technical plots. This is a plot of the entire hydropower sort of operating range. On the x-axis, we have head up to 2,000 meters of head, and then flow up to 1,000 meters of flow per unit. We are focused on low head hydropower, so basically hydro less than about 40 meters, and the green stars are turbines that we've already built and tested. The yellow stars are turbines we're actively designing or have designed this year. And as you can see, if you look at the diagonal blue lines indicating size, we are now designing turbines that are over 20 megawatts and up to 50 megawatts in size for individual turbines. And that's the concluding point I wanted to make, which is that what we are working on and creating is a design method for fish-safe turbines that applies at a huge range of scales from small to large, and can really allow for actionable options to significantly improve the sustainability of our hydropower resource. Thank you.
Thank you. That's really amazing stuff, if you ask me. We've had a couple of questions, not too many, so please keep your thinking caps on. And actually, we're not all engineers out here in the audience, so that's kind of fun. But let's look at some of the bigger questions. Mark was asking about what happens behind dams and the sediment that gets left there, and I kind of would like to also. He was asking specifically if dredging is economical or practical, but I would specifically like to put that in the context of the fact that we're trying to remove, there has been a movement to remove old dams, old smaller dams, to restore basic river flow. So the question then becomes, taking down some of these older dams, what are the big benefits and the pros and cons versus the maintaining these and restoring hydro, the benefit that producing electricity from these could give us?
Well, I'll take a stab at that and then let Abe and Gia comment. I think, as I said, it's not a one size fits all. You know, each system would need to be evaluated in terms of how much material is accumulated, how feasible is dredging, and it could be that there would be, in some cases, kind of a two-tier approach where the existing dam is removed. Natural stream flow for a while can remove some of the sediment rather than digging it all up and having a lot of trucks going through a small town in New Hampshire, for example. And then once that sort of flushing of the sediment has happened, building from scratch a new system that can deal with the fish issues, the sediment accumulation issues, the water temperature, and all of the aspects that I was talking about. Whereas some of the, maybe in another system, they're depending on the sedimentation being, it would matter whether what would be done as a case-by-case basis would be my answer.
Yeah, so, and maybe this is a little bit more context. I think there was some work done by the International, I think, Commission on Dams last year, and there was an estimate of something around like, I think 12 or 13% of the storage capacity of the largest dams in the world, something like the 50,000 largest dams in the world or something like that, is currently lost to sediment, and there is that is expected to grow. So that's current today, about 13% hit. And then it is expected to grow over the next several decades, by maybe 2 times that. Now there are again, very case specific. One thing that is actively being looked at in design is basically ways in which you can incorporate flushing and have more, straight flow through facilities. Some of the work that we're doing with a couple of developers where really revolves around changing the design philosophy for hydro as opposed to building single large, very concentrated, large reservoir style projects, instead going to a more distributed approach. These are still larger projects, so it's not necessarily, tiny hydro, but we're talking projects that are, say, 5 to 50 megawatts per individual site, but where the reservoir now is really not a major reservoir and is designed to flush, to maintain a more natural flow of sediment through. So
yeah, I would also jump in that as you have these larger reservoirs, larger surface area, the water loss due to evaporation and the warming temperatures becomes significant. So that's something we're all aware of. And another issue that would be considered on a case-by-case basis is, what's the quality of the sediment? Has there been a lot of industrial waste and everything else that's in the sediment, and how would that need to be dealt with?
The whole pollution problem. Good. So there's trouble behind for hydro and there's trouble ahead for renewable energy. So anyway, good. Abe had thought that where is it? Answer live. You had wanted to pick one of these questions out, Abe?
Oh yeah, that was an accident. I'm sorry. So I went ahead and typed the same answer to another person who asked roughly the same question, but X-Wing had asked about the efficiency of our turbine designs compared to conventional ones. And the bottom line is that our hydraulic efficiencies are competitive with conventional equipment. We are able to produce designs that have hydraulic peak efficiencies between 90 and 92%, possibly as high as 94%. And that's surprising, actually. I think we thought that you would have to accept some significant efficiency penalty to have really blunt leading edges and maybe these odd forward swept shapes. But it turns out that it's entirely possible to design extremely efficient shapes. even with those new constraints added.
Excellent, excellent. Kath asked about the cost compared to regular design, which you said your turbines certainly are mechanically, you just said equivalent. I also was curious in a whole, I mean, if you could scale to replacing every dam that had hydro or some of the dams that didn't have hydro, how much would that contribute? If the cost is similar, is it worth us trying to expand this?
Yeah, so maybe I can just add some stats. So they're about something like at 80 to 90,000. It's a little bit of a range as you get to the max in the US of existing dams. Of the existing dams in the United States, about 2% produce hydropower today. So a very small fraction actually of the dams in the US that produce hydro today. So there is definitely opportunity to put new hydro at existing non-power dams, given that there are so many of them. And that has been studied at length by Oak Ridge National Lab and the DOE and the industry. And the rough metrics are that there's something like 13 gigawatts of potential at the existing non-powered dams in the United States. Now, our assessment of what's actually economically viable of that 13 gigawatts is probably 50% of that. And the reason is a whole set of factors. Not all of those dams are proximal to interconnection locations. A number of those dams have very small resource. There's a lot of many small structures that just don't have enough energy that they would produce to make them economically viable. So there's a range there. So our estimate is, yes, we can get new hydro from non-power dams. That's about, we would put it at, call it 5 to 6 gigs. There is also something like 100 to 150 gigawatts of so-called what's called new stream reach, so true new greenfield hydro potential in the US. It's actually quite a fair amount of technical resource potential. Of that, some work has been done to screen it down to something like 65 gigs of what would be like probably more realistically achievable stuff that's not in, for example, wild and scenic river, in various, conservation and protected areas. Of that 65 gigawatts, getting it unlocked, we think is possible with the technology we're developing, but is something that's, still, we're just seeing the initial start. So in the last 5 years, I think we've seen something like several tens of megawatts of true new greenfield hydro proposed in the US. That's not pump storage. There's a ton of new pump storage currently being proposed. So that's just some metrics around like resource potential, what could be unlocked. In terms of cost, in general, upgrading the existing fleet is your lowest cost way, because you already have the existing investment in the interconnect and the infrastructure, et cetera. So it's, that is generally, you're talking, all in, hundreds to maybe $1,000 a kilowatt of investment. It's still not tiny, right? To replace a turbine is a couple $100 a kill, is hundreds of dollars a kilowatt in upgrade costs. Then when you talk about true new build at non-power dams, of which now we have some data. So the latest report coming out from the DOE on hydropower market stats is showing that the cost to do new hydro, that is, call it 5 to 50 megawatts per plant at non-power dams, is coming in around $6,000 a kilowatt installed. So that just to give you some metrics. That sounds expensive, but in general, the capacity factors for these projects are well upwards of 50 to 70% capacity factor. So your delivered LCOE for these projects is generally coming in without subsidy, somewhere between, call it 4.5 cents, so $45 a megawatt hour, to maybe 8 cents, $80 a megawatt hour, unsubsidized. And then because hydro, as a result of the Inflation Reduction Act, also now benefits from the same investment tax credits that wind and solar do. And so once you take into account those investment tax credits, just like wind and solar would do, you can see delivered costs post subsidy come in, call it, I would still say like low 4 cents, maybe high 3. I don't see new hydro coming in frankly under $40 a megawatt hour, just to be blunt. Not that you're going to build and get financed, but somewhere in the 4 to 6 cent range is, I think, achievable post subsidy. And for a renewable energy resource that is basically delivering, capacity, black start, ancillary services, reg up, reg down, in addition to generation, that's a pretty great cost-effective resource. I was kind of lumping together some answers there just on cost and economics.
No, that's great. That's great. Are your turbines the size of the large hydro plant turbine setups? I mean, they have multiple turbines across the dam. Is 50 megawatts the size? Would that be not interchangeable? Could that be a replacement, or are the big dams bigger?
Yeah, so hydro is a logarithmic resource, and so for someone, a 50 megawatt turbine would be nearly the largest of the fleet, and that's kind of true in North America for low head hydro. In China, there are individual turbines with 800 megawatt shaft power.
Wow.
So that's peanuts compared to that type of a turbine. But in North America, a 50 to 70 megawatt individual turbine would represent a large turbine for the vast majority of low head hydropower in basically North America.
Okay, but you won't be able to fix the Cooley Dam turbines with your 30-meter or 40-meter head turbines.
Yeah. So the majority of hydro energy comes from projects that are above 40 meters, and that's another and pretty important problem. So we are not a silver bullet, but we're an important tool and a pretty substantial and important part of the hydro market. But yeah, there's a lot of other parts of the resource that have their own characteristics.
Okay, we have time for a couple quick answers here. The Jean is actually typing an answer to Trout Unlimited. How do you would you care to just talk it out, how to convince Trout Unlimited that it might be a reasonable thing to have hydro, especially if it's smaller hydro, or don't you think it is?
So I think that we actually have the same view as most environmental groups, that small size is not really the right determining factor for what the impact of a hydropower plant is, or dam is, frankly, on the water. You have to look at what are the actual impacts with respect to groundwater recharge, like a whole host of things, not just fish, indigenous communities, local communities, et cetera. So I think that, anyhow, there's been a huge amount of work over the last number of years by the industry to work with Trout Unlimited, as well as a number of environmental NGOs, American Rivers, WWF, TNC, TU, CalTrout, Riverkeeper, et cetera. All of that has been wrapped up in an effort called the Uncommon Dialogue that was critical in resulting in environmental community support in the bipartisan infrastructure bill, which passed $2.3 billion of federal funding to go towards hydro in the US. It was like the single biggest chunk of federal funds, frankly, that's gone into the hydro industry in the last 10 years. And also that support was necessary to get hydro in as part of the Inflation Reduction Act alongside the other renewables. So I think we're seeing some good work. I think there's still quite a lot of skepticism, and a lot of it warranted. And at the end of the day, we think it is possible to deliver real improved solutions, and value. I guess I would just say we value a very deep, active engagement with both the environmental groups and the regulatory agencies as we figure out ways to use innovation to deliver some progress.
That is really great, and we've almost come to the top of the hour. So I really want to thank you folks for coming and talking to us. This is a fascinating and important part of our discussion in our transition to clean energy, or no carbon energy, let me put it that way. And I just wanted to remind folks that that EESN does do monthly webinars. Sometimes we miss a month. We do not have one planned yet for September, but our website will always announce not only our events, but events being sponsored by other alumni groups. So I encourage you guys to come back to the website, see what's going on. We will be planning something for September and October, and it's been pleasure having all of you here. And Gia, Abe, and Diane, thank you ever so much for sharing all your insights and help with us. Thank you.
Thank you very much.
Thank you.
Thank you. It's been a pleasure.
It's been fun. Good. Bye now.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.